So hello, everyone. It's very nice that you join us today for this first webinar of the IRTC Junior Board. And we're very happy that Martin Hillenbrand has organized that and that we have Dr. Barbara Reck from Yale as a guest speaker. I think some people are still coming in, but I'm starting with a very short introduction. This webinar is organized by the IRTC project. In case you don't know the IRTC project, IRTC is short for International Roundtable on Materials Criticality. It's a project supported by EIT Raw Materials that has been existing since 2018. It is a network of internationally leading experts in the field of critical raw materials, from research, industry, also policymaking. And the purpose of the project is to connect the research and practice on criticality and critical raw materials to foster the international exchange and also to raise awareness towards the topics. We publish joint reports, joint academic articles, and we host an annual international conference, the next edition, and you're all kindly invited to join. That will be in Ljubljana, Slovenia, next February, from February 19 to 21st. We also have a training program. It's ISO certified, where people are educated to be a raw materials risk manager. And you can visit the website for more information. Since earlier this year, we have a junior board. So we have this really big advisory board of, I'm not really sure, 45 international experts. And this year we thought it would be very nice to also have young voices integrated in the project. And we had the call for application for this advisory board, and we're very happy that we have an excellent composition of junior people in the critical raw materials field from all over the world and with very different backgrounds. And this junior board, luckily for us, has been very active already in the first few months. And they are involved in the conference, they're involved in many other things. And one thing they're also involved in is in hosting these introductory webinars, and the first of which is today. And with that, I will hand over to Martin, who's today's organizer.
Yeah, thank you. So my name is Martin. I'm one of the IRTC Junior Board members. I'm a PhD student at the University of Bayreuth, and I will be your moderator for today. With that, it's a great pleasure for me to introduce here Dr. Barbara Reck from the Yale School of the Environment, one of the birthplaces, if not the birthplace, of the concept of raw material criticality as we know it today. And Barbara will be talking today about the fundamentals of critical raw materials, CRMs, the assessment of those, and the role CRMs play in the global resource management right now. So a topic that has become very topical again in the recent days. Those of you that know the news know what I'm talking about. So with the export restriction of raw materials such as gallium, germanium, and antimony rising, yeah, hopefully we will hear something about that too today, Barbara. And yeah, this session will lay the groundwork for the future discussions at the IRTC conference, but also with those webinars that will follow this first webinar here, and also with all the complete landscape of CRM and criticality assessment. And with that, it's my great pleasure, as I already said, and an honor for me to hand over the floor to Barbara Reck. Yeah, Barbara, the floor is yours. Thank you for being here today.
Thank you very much, Martin, and also Alessa for the introduction, but also for the kind of invitation to have me here. Yes, so the idea really of this talk is not to give you sort of an overview what's going on, sort of what are the latest developments and political assessments, etc., but really talk about the concept of critical raw materials itself and how it developed, why people got interested in it, and so the focus is more historical, let's say, and introductory than anything else. And Martin just mentioned, this is to the left, the headline from 2 days ago in the New York Times, China bans rare mineral exports. And then in the subtitle, you see words like supply chain warfare, which sounds pretty dramatic. To the right, this was 2 months ago in October. Similarly, the sort of the restriction to minerals that are needed in computer chips. And I think this sort of these two headlines in a way summarize exactly what we do not want. So the idea was to, or when the entire sort of concept or sort of this idea dawned on people in the late 2000s that this may be coming at some point, which at that time had not yet happened. But the idea was to say, okay, so how can we prepare for that? First of all, we need to know what is critical, what could potentially be critical, and then how can we basically create resilience in the supply chain. I think that's really what it's all about, trying to make nations more resilient, industries more resilient at all places, and so that these sort of short-term shocks in the system that are really, or that can be really disruptive, both in terms of supply, in terms of price, do not happen. So that's a little bit the background from 2 days ago, basically. And I tried to sort of summarize this, what triggered this interest, and came up with 5 main sort of themes, and there were more at the time, but those are sort of the key ones. One is a very simple one. We've been using metals over the past 100 years, and metals come in ore bodies, in mines, and these ore bodies are limited. It's a limited natural resource. It's not something that gets regenerated annually or something like that. So the moment you find a nice copper mine, like in Bingham, I think that's the Bingham mine in the US. So, and you start digging, in the beginning, you get beautiful ore grades of 3%, 3.5%, and life is easy, let's say. But then the more you dig into these mines and the more they're being exploited, these ore grades go down over time. So the simplified diagrams to the left basically show on the x-axis, it's the timeline, and you can basically say the last century or so for any of these. So the more metal you produce, the lower your ore grade is. And that is simplified, but overall, that's a concept that we find. And also, and the other thing that comes with it is that, yes, geologists keep digging, and they may find something, but if we find the greatest mine for any metal that you're interested in under New York City, it's very, very difficult to get that mine ever out of the ground because there's just too much, and that's the extreme example. But similarly, this not in my backyard concept is something that is no longer just happening basically in the more industrialized, richer nations who really don't want to see any mines anymore. But it's across the world because people no longer accept big environmental impacts that can come with mines, and therefore so if a new mine is opened, mining in general also has become more expensive because there have to be safeguards in place that make sure that the environment does not get polluted and that the health of the workers also is ensured. So that's sort of the general concept. Primary mining, yes, it's possible. Yes, it continues to do so, but there are costs, and these costs are growing. The second point is that the more modern technology gets, the more fancy basically its raw materials also become. So we have in solar cells, we are using gallium, germanium, indium, elements that were not used much before. In the magnets of the wind turbines, we have neodymium. So in the cell phones, we use more than 50 elements. So this is a general concept across any technology. And this was, somebody made this sort of 15 years ago, very simplified, basically saying, well, there was the Bronze Age, well, that's not on this chart, but, and then there was the Iron Age, and those were basically the main metals. And at some point, they added a little bit of lead and copper, that was in the 1800s. And then you see in the 2000s, and nowadays it's really the entire periodic table that is being used in one way or another. And just here the example on electric vehicles. So in the batteries, there's a lot of talk about lithium, cobalt, nickel, and manganese, plus graphite also. You have the permanent magnets. You have with dysprosium and neodymium, two rare earth elements. You also have here lightweight materials. That's typically aluminum instead of iron or steel, but also with magnesium alloys, and I'll get to that example a little later. So material complexity has grown and continues to grow because everything is about optimizing performance. And often it's also a trade-off. So yes, here you need more fancy materials, but so that's sort of the downside, but overall there's the big benefit, of course, of lower emissions during use. And here, this is a chart that was the IEA a few years ago, had 2 years ago, actually, they had their first report, the role of critical minerals on clean energy transitions. And you see on the top here, so kilogram of sort of how many different sort of metals or materials are in a electric car versus a conventional car. And this does exclude the steel and the aluminum and just looks at the specialty metals. And you see a conventional car, well, there's a little bit use of manganese and copper, but not much else, while nowadays here you use the entire range of those elements. And power generation here, the same thing. Natural gas and coal were just a few specialty metals. And while when you're going to offshore wind or even, well, solar, you have simply more different metals that you have to worry about. And at the same, so we need more and more fancy metals, but at the same time, we realize that the recycling of elements or of metals, at least in the past, has really been limited to the base metals, to the common metals like steel, aluminum, and others. And I'm using here the example of nickel. Nickel is among the big metals, probably or next to steel, one of the most recycled elements because it's extremely expensive. It's expensive to refine, to produce, etc. And here, the diagram shows the entire material cycle for nickel. So for the production, so you have in the left lower corner the mining. So here would be the ore extraction, and then the ore gets concentrated into a smelter. The smelter makes then, and refinery, they make finally the refined metal, which is being used in fabrication to make steel, stainless steel, to make super alloys, and also some nickel sulfide for the batteries. You have manufacturing where those intermediate products are being used for washing machines or for buildings, or in cars for some components. And then you have the use phase. And here you have, and what comes out of the use phase is basically the discarded, the end of life flow here, the nickel scrap. And here in waste management, that gets sorted. Ideally, it goes back to the system as old scrap, as recycled scrap. But you see, it's only 2/3 of sort of what goes in here. The rest is being either landfilled or downcycled to other material cycles. And as a result, when we calculate the end-of-life recycling rate, we get to 63%. Well, that's more than 50%. That's pretty nice, but it's still far away from this concept of metals being infinitely recyclable and 90% recycling rates, 100% that people dream of, and it's just not happening for a number of reasons. And it's actually a little bit more sobering if you just sort of think about it, if you look at the entire cycle, if you include the other losses that happen. So 100% here would be what comes out of the mine, the 1500 here. But then you have losses to tailings, you have losses here to the slag that are already quite substantial. And if you take this as 100%, what's in the ore body, it's actually only 52% that gets recycled because you have these losses along the line. So saying that, yes, 50% recycling is maybe pretty nice, but it's still, there's still quite a bit lost. And then we looked at this for all the elements of the periodic table, all the metals and metalloids. So those were 62 elements. We did this in a 3-year project under the heading of UNEP's, United Nations International Resource Panel for Sustainable Resource Management, that was founded in 2007. This was one of the first reports. It was published in 2011. And the way we tried to understand this was to just bin these elements into these 5 groups here, where the most recycling is more than 50%, and that is in dark blue, while the in 1% or basically no recycling would be shown in red. So what we see here is that the 50% and more, yes, we see here the nickel, we see iron, cobalt, copper, zinc, but they are limited to maybe a third of the, or even less of the periodic table. And more than half of the periodic table so this was reference year 2008-9 or so, there was basically no recycling. And when this report, and then you have some sort of in between, and sort of not being recycled, you have here gallium, germanium. I mentioned these, and actually Martin mentioned them. Those are the 2 elements, or 2 of these the elements right now that are being mentioned in this latest sort of trade sort of dispute that's happening. But also we see indium here. And the rare earth element not being recycled or not at all. And we did a follow-up study that looked at, well, why are these non-recycled metals, why are they not recycled? Because we felt, well, are they really all the same? And what we realized is, after an in-depth study, and I'm not showing this here, is that some of them, for some of these specialty metals, there's just their use is so relatively young that their recycling technologies do not exist. While for other metals, it's more like, well, recycling technologies exist, but the economics are just not making any sense. You don't get to economies of scale if you use something only in a few grams here and there, and then the collection and everything, it becomes a huge logistical headache also. So yes, so there are differences in this, but yet as a result, when this was published in 2011, it made quite a splash, because people were like, oh, I think we have a problem. And as a result, particularly in Europe, there was a lot of research that got started in, well, how can we basically improve this? How can we develop recycling technologies? How can we improve the logistics, etc.? And there is no comprehensive update, but I would say a few of the red ones, they have moved at least to orange or yellow by now. Then the 4th point I want to mention, sort of that also what we realized, having worked on the main metals for quite a few years, is that, well, the mining of metals is actually complex in the sense that, yes, you have the elements that are mined for themselves, the base metals. You have, again, nickel here, tin, zinc, lead, rare earth elements. You have here the copper, but then a lot of the other, the specialty metals, there is no tellurium mine in the world. There's no lanthanum mine, because those are really byproducts of of sort of one major metal. And what that means is that if you want to increase really quickly your, say, indium supply for something, well, you get indium from tin and from zinc mining. But if the demand for indium grows dramatically for flat screens or so, that does not mean that the zinc mines or tin mines will mine 1 ton more than they need to, because for them, indium is really just a relatively minor economic aspect. And that's something that makes sort of the typical supply and demand dynamics just also a bit more complicated. And again, this is the second of 3 periodic tables that I show you today. These are again here colored, shown. So in blue are those elements that are really mined for themselves, where the supply and demand dynamics work beautifully. So if there's more demand, you mine more, period. While in red, you have those that are really 100% just companions, so as byproducts. So again, gallium, germanium, indium, you have them here. A lot of the rare earth elements, I realized I was wrong. So lanthanum is actually, to some extent, and I apologize for that, is used to some extent also as a primary material. But others here, zirconium, hafnium, rhenium, they are just all byproducts. And then the final thing is, again, coming back to the introduction, is minerals are not distributed evenly across the world, which means some happen to have more, others happen to have less. And if you are a modern technology, a modern industry, you need these elements no matter where you are, and that leads to potential trade disruptions. And here, these are headlines from the first rare earth crisis. This was in 2010, when for 2 months, because there were geographical disputes between China and Japan in the sea, and as a result, for 2 months, only 2 months, China stopped exporting rare earth elements to Japan, which had huge impacts on their automotive industry. And just one I find rather interesting anecdote is one of the rare earth elements, europium, is the only pigment that gives you a really beautiful red. So for 2 months, Japanese car makers had really trouble making red cars. So if you ordered a red car somewhere, you likely had more trade delays in getting your new car than if you ordered a blue car, for example. So those were things, and that's basically also this crisis in 2010. This is when really a lot of people basically woke up and said, oh, so one is, when am I the next country? So instead of just Japan, when am I the next one? Or the other question is, well, what are the next rare earths? What's coming in the future? And those sort of questions came up. So again, this, just to summarize this first part, we have decreasing ore grades generally. We need more and more materials. We don't recycle a lot. And the mining is often of specialty metals is often as a byproduct. So it's difficult to just quickly mine a little bit more when we need more. And you have this issue of the uneven distribution across the world. So the next question was, now that everybody was convinced, or we were convinced, we felt, well, this really has to be done. How do we do it? And the very, very first publication in this respect came from the US National Research Council. It was published in 2008. So starting in 2006-07, maybe a dozen or so experts came together. Professor Gradle, Tom Gradle, who founded actually the entire research at Yale, and I should have mentioned that at the beginning. He was one of the panelists. He was on that expert panel, and he was one of this team who created this chart. And he was also the one who in the late 90s started the stock and flow project at Yale that did these material flow analysis of the main metals at the time that eventually led to this dawning of, well, we are running into some problems. And the way this research council looked at criticality after really talking this through, they felt, well, we have two potential problems. One is supply risk. So there is just not enough material available. And that would be if the mines across the world, they are basically almost exhausted. And there's this feeling that the supply itself is limited for various reasons. And then on the y-axis is, well, that may be true for some metals obscure metals that nobody's interested in. And then, yes, you may have a high supply risk, but if you don't care about the metal, your impact is still low and it doesn't really matter much. As opposed to if you have something that you care a lot about because all the economy is really dependent on it. A lot of industries are dependent on it. So what is the impact of the supply restriction? And what they said is what you really want to avoid is being in this region of danger here with a high supply risk and a high impact. So they then continued and said, well, let's take a few examples. How does that really work? And they were geologists and experts from various fields. And so they had a pretty good sense. And they came up with this diagram. Again, this was the very, very first criticality assessment, although I wouldn't call that assessment. It was more like an informed gut feeling, maybe. And what you see here is, so first of all, they did not pick iron or aluminum. They looked really at the specialty metals, at those that are potentially really the most affected here. And we see here, so copper is included, and that is found here as a low supply risk, but of high importance, relatively high importance, as an electricity conductor, etc. But the low supply risk was because copper is very relatively evenly distributed across the world. So a lot of countries have it, and you don't have this sort of accumulation in just one or two areas of the world. So that's why, yes, it's really important, but it was not in the region of danger. And the opposite was true here. We see here, these are the platinum group metals, and on top of everything was rhodium. Rhodium is primarily used, or at the time was primarily used as a catalyst in diesel vehicles, and there was really no substitute for that. So, and a lot of engines, they run on diesels, and there was just but also other technologies, and there was really, rhodium was very unique basically in its characteristics. And you see others here, also platinum very nearby, and the rare earth elements here in light blue also sort of on this level, because this substitution, etc., is all difficult. So this was published in 2008. Again, Tom Gradle from our group, he was part of this, and he realized, well, this is a really big problem, but also we have to look into this more closely, and we have to sort of move on from an informed gut feeling basically to a scientific methodology. So that was the goal. So how can this really be done? So what we did is sort of we applied for funding by the US National Science Foundation, which we got, and that was funding for at least 3 years. And I should really mention that the entire work was based on those some 10 years of experience, where we really made these detailed looks into copper, zinc, steel. We had a silver cycle, lead, chrome, nickel I showed you, stainless steel, and rare earth elements, and I may have forgotten some. But But what you see, all these elements that we had looked at so far, they were all the main elements, those that are mined for themselves, those that have industry associations where you get good data. But the moment you're talking about gallium, it's really, really hard to get to data. That's sort of another issue that we faced. And what we also realized is, yes, it was wonderful to have the funding from the US National Science Foundation, but that alone just wouldn't do the trick because there was so much to do, because our goal was not only to develop the methodology, but then to apply that methodology to all the metals and metalloids in the periodic table to really get a sense, well, who is more critical than others. And so we created this industry consortium where we had members from, this was always maybe less than a dozen, maybe some 10 members at a time. And it was changing. So for a few years, and some were only part of us for 2 or 3 years. Others sticked around for the sort of 5 years or so that we worked here. And it really included really large ones, including large automakers, large industries, to very, very small one that had a very specific question, and they realized they wanted to do something. And so we met once or twice a year, and they provided their feedback. So, and that was really helpful, because what we tried to do is to develop a methodology that was transparent, public, based on publicly available information, reproducible over time, but also relevant to industry and sort of relevant to them. So what we did, we started in 2009, and this is a typo. This should be, base year was 2008, of course. Sorry for that. And what we realized is the methodology, metal criticality is different for whom you ask. So, and we developed it therefore at 3 levels, so with slight differences. So corporate level, national, and global. Corporate level is because if you're a company who doesn't need rare earths, then the rare earths are not critical to you. While if you need them, then rare earths can be very important. National governments, they look at what are the industries, what is sort of important in your particular country, and and the politicians who then make the decisions, they have timelines of, say, 4 or 5 years. So this was sort of a medium term where we looked at things. While global, we really said, well, here we are looking at sort of at global level, and more long term for the next 50 years, are we as planet Earth running out of rare earth elements all over, or is it just that, no, we have a few countries that are running out, but overall there is still always something available. So we felt that criticality very much depends on who asks the question. And so we did this, eventually published this in 2012, and I'll walk you briefly through how we did this. And just again, to repeat this point, that these analyses that we did, that we developed with the methodology, were really rooted in these material flow analysis that we had done in the past. And here, this was rare earth elements. We had a PhD student who started in 2009, her PhD, or 2008 even, on rare earth elements. These 3 articles were published in 2011, right around the time that everybody sort of said, oh, this is interesting. And she also then wrote a paper on or a study where she applied the methodology just to the rare earth elements, and not just as a group, but really individually to all the elements. So not just so separately analysis for neodymium, dysprosium, lanthanum, etc. And then what we realized, so we said, okay, how do we do this? So first of all, our idea was we have to sort of normalize risk somehow. So we ended up with a scale between 0 and 100. So 0 was no risk and 100 was high risk. So any information that we would find was normalized to the scale. The second thing, having really discussed this quite a bit and sort of thinking through what is this, what is that, what we realized is we felt in this original report that only had the two axes, we felt the environment did not really fit in either, because it was somehow either included in supply risk, but it was also relevant to the vulnerability. So we ended up having environmental implication as a separate axis. To the supply risk. Supply risk, we binned it into geological, technical, economic factors, social and regulatory, and geopolitical. Geological means depletion time or companion metal fractions, so this issue of the byproducts, policy potential, human development index. Yeah, and I'll basically, let me say here how we got to these. These three here in red, these are existing indicators that are developed by different bodies, and that are also repeated every few years, and that, for example, political stability, that sort of say, well, which country is more stable than others, and which are sort of more of concern. Because if you have a lot of a metal in an area that is politically unstable, it doesn't help you much. It still means that you may not get it. And global supply concentration, there is a so-called Herfindahl-Hirschman index. We had to put this upside down, sort of, or that to normalize it to 0 to 100, we needed to go through a few extra steps, but it's basically coming from this here. And then you see here these two, depletion time and companion metal fraction. These were our own analysis that were basically based on these material flow analysis that we've been doing. And here, human development, and I see I have to run a little faster. Human Development Index, published by UNDP, some measures human development, focusing on health, education, and living standards. And then comes up with this kind of world map. That's what's the world map for 2008, sort of what's the situation. World Government Index quantifies political stability, is published by the World Bank, includes national economic political factors, economic distress. And Global Innovation Index, very important. So even if you run out of a metal, how likely is it that your country, your industry is able to innovate and find substitute for examples, or sort of get around the problem? And that means the higher your R&D capabilities are, the more likely you are to be able to deal with that. And that is something coming at the, so these two were supply risk the first time, and that really helps with the vulnerability, susceptibility here. And that is here. Yeah, no, the World Government Index was this one here, also with a similar world map here. And vulnerability is where we say, we basically say three things. How important is it? Is there a substitute available? If it is important and we no longer have it, can we use another material? And then susceptibility is, again, this sort of, can you innovate yourself out of the problem? But also, how important are you on imports? Are you relatively independent because you happen to mine the metal in your own country? Or are you more important, basically, or dependent on imports? The importance itself was material assets, which basically means if you are a country that has used and mined or used a material like, say, steel or for a long time, then you have stocks in your country, meaning you have a lot of cars driving around, you have a lot of machinery that at some point will become available for recycling, and then you may not have access to primary raw materials, but you may have access to your own scrap, and therefore dampen a little bit the need for primary new materials. And then also what's the national economic importance here. And here we had as an existing indicator the Global Innovation Index. Then we have substitute availability that comes from the supply risk of whatever we're interested in. So if we are talking about copper for electricity, and we know, well, aluminum could be another substitute for electricity transmission, we would look at the supply risk of an aluminum criticality assessment. So we are combining, and that's why we realized relatively early on, doing or applying our criticality assessment just to one or two metals wouldn't really work, because we would always need to look into, well, and what is the substitutes, and how does it look there? And it's, in the end, it's a network of these 50 or so 60 elements that's really, they are not independent of one another. And that's why we, in the end, ended up also looking at all of them. Environmental impact ratio comes from our environmental axis, which is basically cradle to gate from life cycle assessments. It's the impact to refine or to produce 1 kilogram of a metal mined to first use, and net import reliance here. One example here that was really important, that sort of stuck out, was a substitute performance. Because a lot of times people say like, well, let's just use something else. And what we realized is, well, that is tricky. We have here the color scale is blue, no problem at all. Substitution is not an issue. Red, it is a big problem. And what's important to highlight here, this is per element, and any element is not just used for one end-use sector, but for a lot of them. So again, we have transportation, we have buildings, we have machinery. You can have all kind of end uses, and this is across all end uses in a sort of weighted average that we developed. And what the key message of this chart is, not a single element is blue, not so that all the end uses of a metal are easily recyclable. There are problems with a lot of them, and some actually are even more difficult to substitute, and that comes back to this rhodium that we discussed in the beginning as an example of these red ones. So putting all this together, this was sort of the national level assessment of our methodology. We have the supply risk, we have the vulnerability supply restriction, and we have environmental implications, where we looked at human health and ecosystem impact. And when we started, we said, okay, we cannot do 60 at the time, and we went by ore family. So we had one group working on the copper, what we call the copper family, another group working on the rare earth elements, etc. And this is the first result that we had. This was published in 2012 for the copper elements. So we have here the three axes. And the results here, copper, gold, and then here the other elements, they are shown as clouds, and that's basically uncertainty analysis. So we ran Monte Carlo calculations in the end across all these many indicators, because this is not a very exact science. It's sort of, well, where do we roughly stand? It's nothing else than that. But what we see is that, for example, copper, it is relatively similar to what we had originally, what the National Research Council also said. Yes, supply risk is low and vulnerability is high. So not that different here. And gold standing out as the only one with a really high environmental impact because of its association with mercury, etc., depending on how it's being produced. And again, here, this comparison, I would say pretty good for a first estimate at the time. And then this is just for you to know that it exists, and it's hard to see anything here. But this was basically the result for all the elements. And again, here's also our copper that we saw before. And the key message here, our region of danger would be here, where all three axes are high risk. And there is fortunately nothing. So that's in a way is good news. However, if you forget the environmental axis, you do see here basically the similar culprits than we had seen already by the National Research Council. And by the way, the coloring is based on how we had grouped them. So we did light metals, specialty metals, iron and alloying elements, here the copper group, etc. But this was basically our approach to making this somehow feasible. Oh, and one thing I wanted to show is here again, rhodium. Also for us, rhodium stood out really as the highest vulnerability of all for this fact that it's not being substitutable and so important for some industries. And just very, very quickly, what we in the discussions that we had when we talked to our friends from, for example, trade associations of the mining industries, and they were really puzzled about all this and said, well, what actually do we want to be critical or not? Because they were like, well, if we are critical, then people will fight for our material and we will get prices go up, and isn't that beautiful? But then basically in the next sentence, it became clear that, well, yes, and people are so upset about that they will substitute away from your metal, and in the long term, you risk reduced demand. So people, but pretty quickly sort of settled on, no, we don't want anything we are involved in as critical. So there was one thing. Then, yeah, I showed this already before, and I think we can move over here. And so in 20, or this was, yeah, Renault, this was an article published in 21, but about 10 years of research at Renault. Renault basically looking at this, well, we don't want to become the next Japan and not being able to get access to rare earth elements, and therefore not be able to build our electric cars. So what they said is they looked very early on to substitution, and they found a way to make their electric motors with a copper wire rather than the rare earths. Here, Nissan, they were able to reduce the use of dysprosium by 40% already in 2012. And the latest, or this was a few years ago, no rare earth magnets at all. Other car makers also trying to reduce their use. So this is all, these are examples from industry. How can you create resilience here? Another example, this was a few years ago, for just a couple of months, magnesium prices went up immensely. Magnesium mostly mined in and produced in China, very energy intensive. There was an energy shortage in China, relatively short. So it became, for the producers, extremely important and really, really difficult. Fortunately, that was resolved quickly, and also so it didn't stay long. But for a moment, people were asking, well, if such a magnesium shortage sort of would continue, what would be the effect on the global car industry? And there was this sort of question, well, geopolitical, should we put in a climate change policy? It's a question that you could ask, sort of, if we are talking about a carbon cap, how does carbon caps affect the availability of energy-intensive materials? And other things is, so this was in 21, the first time that the IEA also picked up the topic of critical minerals, because it realized they were only talking about clean energy from, and simply implying, or early on sort of thinking, well, if we need more solar, we create more solar, no big problem. And there was this realization, well, there may be raw materials barriers there. So, and that's why it's now well embedded in their aspects, and I showed this graph already, and also World Energy Outlook for the first time had a chapter on critical minerals in 21. So this was a quick run through. I'm sorry, Martin, I took a little longer than we had discussed, we had said, but here we are.